These stuff I will not talk about. This is just example of how the tree algorithm can be implemented with KMPR. The feedback has to be adjusted. This is easy and boring stuff. Maybe this analysis I will talk about, and then I will introduce the moment generating functions shortly. And maybe I will talk also slightly about the Mellin transform that is related to the analysis.
I'm personally exactly interested in how you model this these resources stochastically and how they interact. Yeah, that's I think.
Okay. So the success in normal tree algorithms with one MPR without KMPR is already modeled, and basically you can see it in the equation 4. In the equation 1, it tells you that the length of the tree, if n is smaller or equal to k, is 1. Because if you're transmitting, and if it's a success, this is what this defines, if n is smaller than k, then it's one slot. You don't need to split at all. It's done. Your job is done. If it's larger than k, which means if it's a collision, if n is larger than k, then you have to start 2 new trees. Okay? So basically, this is simple and super easy to understand. Basically, you have 5 users, and then it's a collision, okay? And the number of slots you have with to resolve 5 users is this slot, which is 1 slot, and 2 new trees, 1 tree with 3 users and another tree with 2 users. And this gives it a nice recursive approach. Okay. I can just calculate the number of slots I need for a tree by just looking at the new trees created from that tree. I don't know, that's too much trees in a sentence. But I think you get the idea of it. I want to calculate how much slot I need for 5 users. I don't count, or I don't need to count what are the all possible outcome of the trees. I can just say, okay, this tree will definitely create 2 trees, either if it's 3 or 2 users, or 1 or 4, or 0 or 5. It will always split, and it will always split into the sum of into number of users that will result in the sum of this number of users. And then I can say this one is I, and this one is n minus I, which has to always hold because users don't disappear. And then I can say, okay, just then I will forget about the first tree and I will look at the new tree. And I will do this until I reach the initial conditions. And this is what makes this tractable. Because I know once I have Li, which is the new tree generated from this tree, that is lower than k, then I can say that ln is 1. I don't have to go deeper anymore. And then by using this, I can just put this recursion back and calculate ln. Ln is a random variable, and now we want to investigate this random variable. We can take the expectation of this random variable. And to take the expectation, we will say, okay, the expected tree length is 1 slot that we have for the collision itself, and then the probability to have n minus I users and the probability to have Li users. And then we take the expectation of it by varying I from 0 to n. The problem is, this is not so easy to deal with. I mean, you can somehow modify it like this by taking n out of this formula, because this is you cannot calculate it because ln is on both sides of this equation.
So, Murat, if I can comment here, I've been exactly dealing with the same formulas, of course. When your variable is in the binomial coefficient.
Exactly, this doesn't work. And then one way to deal with it is then to take it out and then move it to the other side, so you have a simplified, not so simple form that you can work with. But since you all still have two variables, it's not so nice. You can do a recursion, but it's ugly. It will take forever. But there is a way to deal with this. And now comes the characteristic function, or the moment generating function, that will help you with this trick. Now for this, I go to the appendix. And then you define a moment generating function. So here we define the moment generating function a bit differently. Normally what you do is you take the random variable and then you put it on top of an exponential. So basically you say e to the s to the ln, or e to the x to the ln, something like this. But here e to the x we consider directly as z, which is the same thing. So basically what you do is, instead of using a linear random variable, you basically convert it to an exponential form. How does it help you? Because while you're summing random variables, it's easier to deal with them because you will be able to multiply them. What I'm talking about is this: since in the previous form we had, since we are talking with 1 plus, sorry, this is n, this is n minus I, and this is li. Since we have generated this, since we have this new moment generating function, instead of this form, we can just write it z to the ln, z to the 1 plus ln minus I plus li. And instead of ugly sums, we have now nice multiplications and z to the li. And these forms are easier to deal with. And this is what we use here. So basically you get, and then you have multiplications. So, okay, now that's the main idea, but now I will tell you a bit detail on how we deal with this, because still the multiplication is not super nice. Yes. So basically we got rid of the 1, and then we have a z multiplication here. We get rid of the sum, and then we have this nice multiplication here. But it's still not at the nicest form. Here it gets a bit too much detailed, which I don't want to bother you with. Where to get rid of the dependence on n here, we take the expectation for a Poisson random variable, and then generalize it to any n value, blah, blah, blah. We take initial conditions out to simplify it. And what is the, okay. And then the nice point of moment generating functions comes only after here. Or we can also take it from here. Basically, once you do those stuff, once you get rid of the initial conditions to clear your equation, then comes the nice part. To calculate the first moment, what you can do with moment generating function is to take the derivative with respect to z, and then plug 1 for the z value. If you take the derivative twice, then you get the second moment of the random variable, which will be its variance. I mean, it's not exactly variance, but it's the second moment, but it's easy to calculate the variance using that moment. Maybe write down a bit.
Yes, so this is actually a question that I have. What do you use this moment generating function for? What is your end goal? Is it the variance calculation, or is it the probability?
It's to have a non-recursive calculation.
Of what?
Of the random variable. Of the expectation of the random variable.
Of the expectation, exactly. So this is what I...
Yeah. So basically the moments go like this: first moment, second moment, third moment. And as you know, the variance is e to the x squared minus m squared. Correct me if I'm wrong, but this is what I remember. Then you can easily calculate the variance from the combination of first moment and the second moment. So basically, and then we take the derivative here and replace z with 1. And now we ended up with the similar stuff, it looks like. But we got rid of the probabilities before it, so it's easier to deal with. And then we assume, so to solve this, so this is a somehow what you call a functional equation. And to solve this, we have to assume Lx has a certain form. I'm starting to feel that you may be getting a bit bored here, but I have to explain these parts also to guide you through the solution. So we assume that Lx has this form and this form. So basically, this is a infinite series in a polynomial infinite series. This part is coming from the initial definition, I think. Exactly, it's coming from this one, where we take the derivative of this and then replaced z with 1. And then this leads to ln, because this was our initial moment generating function for ln. And taking the derivative of this and replacing 1 in it gives us the expected mean, expected length of the tree. So basically, this is what we are trying to extract out of this complex form. And then Lx has this form, and then we assume that it also has that form. Okay. To take ln out, we equate these two numbers and say, okay, once we have alpha j, we can calculate ln. And now we are striving to calculate aj or alpha j. And what we do is we plug this equation in this one. And also move these guys to here. And basically you have on left side the alpha, xn, blah, blah, blah stuff. And on this one, just this one. And basically the idea is then afterwards expanding the negative exponential also with polynomial factorial. Let me also write this down. This is also some trick we used a lot, or we need to use a lot in this. Is equal to sum of n, or n equals 0 to infinity. Please don't delete everything. Minus 1 to the n, x to the n divided by n factorial. This is a series expansion of exponential function. And then you use it for this part, because we just want to have x to the n's in this equation. So basically you see this is e to the minus x. And this part was there already. And then you have to somehow simplify the sum also using some tricks. And then at the end you have on both sides some alpha n to the xn and some values to the xn. And then you can say, okay, alpha n is equal to these values divided by these values. And once you have that, then you can use this equation to somehow extract the coefficients of ln, and then you can write ln from this formula. And then this is what you write, and then you're happy that you had no meaning in your life, but finally you found something. Then you later on simplify it further by using some tricks. Maybe these are interesting for someone. This is some tricks we found also to simplify a sum of n choose case, some combinatorics. if you have -1 here, then it